We will wait for some more time. We'll start at 6. let's get started. So this is applied thermodynamics course. So the first week is on your control volume, and we're doing an entropy balance for control volume, and we'll see some numericals on this. And with going ahead, the next weeks will be the next week is also of entropy control. We'll continue with that in the next week. And to start with, I'll give you a short introduction how to do the energy balance and your first flow balance and the entropy balance. Give me a second. I think my system is not responding. Okay, so sorry for the delay. Uh, so what I have here, first one equation is your flow energy equation. So suppose you have a control volume here, and you have some mass coming in and some mass going out, and you also have a heat transfer and work transfer. So this is how the equation turns out to be. So if you see this can be brought down to your control system as well. So if you assume that your mass flow coming in and going out is 0, then you have on the right side Q minus W equals your change in internal energy with respect to time. So and if you integrate, you will get your first law for control system. So you have Q minus W equals to delta U, and similarly for a flow equation, and if you are making it steady flow, so that's it, the amount of fluid which is coming in and going out, it's not varying with respect to time, and so your dCV by dt will also remain same, so not vary with respect to time. So your right hand side will become 0, and you want to get is the steady flow energy equation. And the fluid which is coming in, you have heat interaction Q. So basically how you can write it, you can write it the energy coming in minus the energy going out equals the change in energy. So that will give you this flow energy equation. So if you see Q plus m dot hi plus the kinetic energy plus potential energy, that's the energy which is coming in, and the going out is you are getting work, and then m dot into h2 exit stream enthalpy, your kinetic energy and potential energy. So that is energy coming in minus energy going out, which is equal to the energy built up in the system. It can be either decreasing or increasing based on the flows which is happening. So that gives you the first law equation. So then you have second law, your Clausius inequality. So this basically from the statement of Kelvin, Planck and Clausius statement, you have defines how entropy happens. So or the second law is basically is derived from there. So they basically say you cannot have a single engine running with a single heat source or a temperature source. So that's not possible, and then you cannot transfer heat from a lower temperature source to a higher temperature source without giving in work. So those were the two statements, and then Clausius gave you the Clausius inequality, so which comes out to be this the cyclic integral of dou q by t, which is equal to 0. So this is true for an irreversible case. So when you have an irreversible system, so that will always lead to an entropy. So that comes out to be dou q by t into cyclic integral is always less than 0. So for our convenience to make it 0, we add a term called an entropy generated. So that is sigma int. So that is the amount of entropy is generated for a process. So this, instead of going through a cycle, what if we write it for a process? So happening from state 1 to state 2. So you can go any of the process. It can be isothermal, adiabatic, whatever the process. So how do you write an entropy change? So again, instead of cycle integral, we change it to a single integral between 1 to 2, and that is generating some internal entropy, and that is equal to your change in entropy. So this is for a process. So now how do you do an entropy balance? So just like your first law, you how we derive from energy in minus energy out equals the energy just stored in the device. Similarly, when derive it for an entropy, so entropy change of the system is equals your entropy transfer, can be because of heat or some other process interaction, and then plus entropy generated due to internal irreversibilities, and that is your sigma int. So this can be written in a mathematical form like this. So dou SCV by dt is m dot I SI is the first you have entropy change of the system, and then that is equals to the entropy just coming in and going out. So similarly what we did, and then because of the process the entropy generated, so plus q by d. So this is happening over the surface, so control surface system, plus your internal irreversibility causing entropy change, right? So this is how you get. So dou SCV by dt is entropy change of the fluids coming in and going out, plus dou q by t plus your internal irreversibility. So here we get, so what is this entropy? So with the third week we will see something called as exergy. So there entropy cannot be physically understood. So it's a concept, but it's very difficult to understand it physically. So if you say you are having your doing some work, so suppose you are rubbing your hand over your desk, so that creates a heat generated, but you are doing some, you are wasting some energy that is not coming as an output, so that energy is wasted. So this entropy is related to how much you are losing your potential to do work. So it is like this. So you once we see the exergy concept, you will understand, you will appreciate entropy better. So that gives you the exergy destroy. So there you will understand the significance of entropy better. So that gives you how much you are losing the potential to for gaining or ability to do work. So there finding this internal entropy generation is very useful. And also you don't know a process is happening, you don't know which direction the process is proceeding, whether process is possible. So everywhere this entropy is always an universally increasing quantity. When isolated system, so that is there is another called your delta S of universe, which is your entropy change in the system plus your surrounding. So this quantity always is equal to 0 or greater than 0. So equal to is when you have a reversible process, but your delta S universe is always increasing. Physically, whatever you do, your entropy of the universe will always increase. So that can show whether a process is possible. So for a if you have these two quantities, system and surrounding. So and you estimate the entropy change, and you find the system entropy is decreasing. So that doesn't generally mean that the process is not possible, but you have to see the whole picture of the universe. Even though the system entropy may decrease, but that will rise to an increase in entropy in the universe. And if that is happening, then that shows that your process is possible. So with this, I hope I have given a short introduction and a recap to the entropy. Any doubts, or else I'll proceed to see some problems over entropy balance. Okay then. So the first question is air is contained in an insulated rigid tank of volume 1000 liters. The air is initially at 1 megapascal and 300 Kelvin. So a valve on the top of the tank is now open, and the air is allowed to escape slowly into the atmosphere until the pressure in the vessel reaches 100 kilopascal, at which point the valve is closed. So the temperature of the air inside the tank is maintained constant during this process by an electric resistance heater placed inside the tank. So determine the entropy generated during the transient process. What would be the entropy generated in the temperature if the temperature of the air in the tank remains constant as a result of heat transfer with the ambient at 27 degrees Celsius instead of electrical work? So first we'll break down this whole problem to steps. We'll see what's happening exactly. So you have an insulated rigid vessel, and that is of 1000 liters, and you know the initial condition of the vessel is filled with air at 1 megapascal, that is 10 bar, and 300 Kelvin. So now they say that the tank has a valve at the top, and you are opening it slowly. So and the air is escaping slowly. So that basically what they want to say is it's a kind of a reversible process, it's happening slowly, very slowly, into the atmosphere until the pressure in the vessel reaches 100 kilopascal, at which point the valve is closed. So the temperature of the air inside the tank is maintained constant. So during this process, so what's exactly happening is you are letting air to escape from the tank. So this is equivalent to having an expansion process. So that's why your temperature will drop, and what you do is you have an electrical heater. So with that you are heating it and maintaining this air inside the tank at a constant temperature. So determine the entropy generated during this transient process, and what would be the entropy generated if the temperature of the air in the tank remains constant. So we'll this is we'll write the first entropy balance equation. So dou SCV by dou T equals your mass of fluid equals coming in and the entropy which is going out, plus your dou Q by T, and the same equation here. So you have to find out the entropy generated. So taking this to the other side, and what you know is there is no mass of air which is coming in. So m dot I is 0, and m dot E is the mass which is leaving. So this leaving and Q, you are supplying Q, and here you see there it was a positive quantity plus integral dq by dt. So what's happening is your Q, you are gaining heat to the system, but with respect to surrounding, the surrounding is losing heat. So since you don't know at what temperature your heat addition is, but you know you can equate that to the surrounding. So you can write this as Q surrounding by T, because you know the same amount of energy is coming from the surrounding. So that will generate the same amount of entropy. So you have dSCV by dt plus mass of air which is going out and the entropy of the air plus Q surrounding by T naught is equals to the entropy generated. So the next equation which we have is the mass. So there is a mass which is changing in the system, because there is no mass which is coming in, but there are some slowly mass which is going out. So if you do a mass balance, so same, the mass coming in minus going out is equal to change in mass of the system. So this will give dmCV by dt is the mass which is going out. So substituting this in the above equation, what we get is dm d by dt. So we are SCV is your entropy and small s is your specific entropy, that is mass times your entropy. So expanding the differential here and substituting m dot E as dou m CV by dou T, and we get this equation, and from this we can find out what is the change in entropy of the control volume for the process. We know that it's at constant temperature, so it's an isothermal process. So from the TdS relation you can estimate the change in entropy. So TdS is your dH minus VdP. So dH is now 0 because your temperature is 0, change is 0. So TdS is your minus V by T dP. So that you have substituted the ideal gas equation, and we get this expression. So this will turn out to be minus V by T, P2 minus P1 plus Q by T naught. So here, since the work which is coming in is an electrical work, so this Q will become 0. So electrical energy which is coming in is work. So your work done on the system, you can, that will not come in your entropy, but heat transfer will generate entropy. So this Q is 0 because there is no heat interaction, it's an insulated vessel, so your Q is 0. So this will come out to be 3 kilojoule per Kelvin. So that is your entropy which is generated during this process. So P2 and P1 is already given. P1 is the initial pressure and volume is also given, 1000 liters, so that is 1 meter cube, and P2 is 100 kilopascal and 1 megapascal. So substituting that pressures and temperature, you will get 3 kilojoule per Kelvin. Any doubts in this? So okay, so then we'll move on to the next question. So The next question is, you have a rigid container, similarly, just like the previous one, you have a rigid container with volume of 400 liters, which is divided into two equal compartments, A and B, by a thin partition. So both compartments contain air, and compartment A is at 2 megapascal and 200 degrees Celsius, and compartment B is at 200 kilopascal and 100 degrees Celsius. The partition ruptures and the contents eventually reach an equilibrium state while losing heat to the ambient at 27 degrees Celsius. So we need to find out the final pressure, heat lost to the surrounding, and the entropy generated. Sorry, my system keeps on crashing. I don't know why. So this you have insulator vessel and you have a partition having two compartments, and both are at different pressures and temperature. So the initial what we do is we know how much is the volume occupied and the pressures and temperatures at which the gases are, and so we can estimate how much mass is present in each of the compartments. So we can use an ideal gas equation. So PV equals MRT, and R is your constant of that gas and not the universal gas constant. So to remove that, and since it's air here, so it will be 288.68. If you are having number of moles, then there you will have a universal gas constant. So you should be careful on that. So here since we are estimating the mass, so M is PV by RT, and P is your 2 megapascal, so 2 into 10 power 6 or 2000 10 power 3, and volume is 0.2, and your R is 288.68 for air and 473. So this will come out to be 293 kgs. And similarly, mass of air in compartment B is given as PV by RT, and P is 200 kilopascal, so 210 power 3, and volume same 0.2, and your temperature is now at 373. So the mass at compartment B is 0.3715 kg. So now we know the partition has been punctured and both of gases have come to an equilibrium state. So we need to find out the final pressure. So there is no partition here. So your final pressure will be similarly PV equals MRT, and your volume is also your combined volume. So MA plus MB times RT2 is VA plus VB. So your pressure, you have found out the masses. So adding that and combined volume is 0.4, and your temperature is given in the question. This is at 27 degrees Celsius. So your pressure is 714.81 kilopascal. So that is your final pressure when the two gases mix. So now we need to find out how much heat transfer is happening with the surrounding. So that we can do an energy balance. So there is no work transfer between the system and the surrounding, but there is heat transfer. So applying the first law gives Q minus W is delta U, or delta E change in energy. So your Q is your change in internal energy, and you can find out internal energy. You know the initial temperature, you know the final temperature of individual compartment masses. So that gives m dot Cp delta T of compartment A and m dot Cv Cv or Cv delta T. And for compartment B. So when we substitute the temperatures and the Cv values of air, and we know the masses, so we get Q as minus 385.39 kilojoule. So that is the heat interaction which is happening with the surrounding. Now we need to find out the entropy change of the system, and the entropy change is given as again similarly. The delta S system is your for the process happening between state 1 to 2. So you know the initial pressures, initial temperature, and you know the final pressure and final temperature. So the gas going through a process between these two, because entropy is again a property, so it will only depend upon the state points and not the process which is happening. So you can estimate the entropy change. So M into Cp ln T1 minus R ln P2 by T1. So this again you get it from the TDS equation. So TDS is dH minus VdP. So substituting the ideal gas equation and integrating it, you get this. So the expression will be same for A and B. So M you do it for compartment A and compartment B. So you get the total entropy change happening between the for the process. So it will come out to be minus 696 joule per Kelvin. So next is the entropy generated during the process. So entropy generated as we know, entropy generated can be written as delta S equals your mass entropy coming in and going out plus Q surrounding minus Q surrounding by T naught plus internal irreversibility or the entropy generated. So rearranging this, you get this entropy change in the system plus Q surrounding by T naught. This equals your entropy generated. So that will come out to be minus 696 for the entropy for the process plus Q surrounding we have already calculated 385.39. So into 10 power 3 divided by your temperature. So this is at 27 degrees Celsius or 300 Kelvin. So this will come out to be 588.63 joule per Kelvin. So we see the delta S is positive. So this process is possible and it's irreversible. So next is a similar kind of problem, but there is a slight change to that. So we'll see what is. So we have an insulated box which is divided into two compartments again, A and B, by a thin partition. In compartment A initially at 10 kg of nitrogen at 500 Kelvin and 500 kilopascal, and compartment B has 2 kg of hydrogen at 300 Kelvin and 100 kilopascal. So now the partition is removed and the gases are allowed to mix and reach an equilibrium state. So taking the box as the system, determine its entropy change. So first we know what is known is here this is an insulated box, so there is no heat transfer. Previously we had an heat transfer, so here there is no heat transfer. So that is the only change here. So your you know the initial mass, temperature and pressure for both the compartments, so that is given. So when you do an energy balance or apply first law for this system, so there is no heat transfer and there is no work transfer, so your Q and W both are 0. So change in internal energy is equal to 0. So your internal energy at the start will always get in, so there is no change in internal energy. So from there you can estimate what is the final temperature after mixing. So that using delta U equals 0, so we find out what is the change in internal energy of each of the components, and that we add it and equal to 0. So we can say, you see here only unknown here is your temperature. So here they have given both molecular weight and the gamma value, adiabatic index value. So we can estimate the CV. So from the universal gas constant, so 3.814 kilojoule per kg Kelvin. So you have divided by molecular weight, you will get the gas constant. For nitrogen it is 296.93, and for hydrogen it is 415.7. Oh, sorry, there's a decimal missing. So I think 384 will be 157. So there's a typo here. So then CV is R into gamma minus 1. So substituting the values here, we will get CV and CP values. So now we can estimate the temperature. So when we substitute this in the expression, we will find out the temperature to be 353 Kelvin. So that is the final temperature when both the gases mix. So next is we will find out the initial volume occupied by nitrogen. So from the first ideal gas equation, we can find out the volume of the compartment having nitrogen. So that comes out to be 2.9693 meter cube, and the initial volume occupied by hydrogen, and that comes out to 24.942. The same MRT by P equals volume. So that is your ideal gas equation, and you know all we find out the volume. So now we find out the total volume. So that is the summation of volumes here. 27.9113 meter cube. So now we estimate the partial pressure of nitrogen and hydrogen in the final state. So partial pressure of nitrogen is mRT by V. So from this we can find out the partial pressure of nitrogen. Initially the whole pressure is because of nitrogen, but once it has mixed, so nitrogen will be exhibiting some pressure, and your hydrogen will exert some pressure. So from the Dalton's partial pressure, so you have summation of partial pressure of the gases equals to the total pressure. So from here you can find out the partial pressure at after mixing. So we know the total volume, and we know the mass of nitrogen and R and T. So substituting that, this T is your final temperature, which is 353, which we have found out previously. So substituting that, we'll get 37.55 kilopascal. And similarly for hydrogen, this comes out to be 105.15 kilopascal. So your change in entropy comes out to be m dot into Cp ln T2 by T1 minus R ln T2 by P1. For nitrogen, it will come out to be 4.069 kilojoule per Kelvin, and for hydrogen, it comes out to be 4.3165. So your change in entropy of the system equal to the entropy generated, because there is no heat transfer, and so the change in entropy of the system equals your entropy generated. So that comes out to be summation of these two, which is 8.3855. So what is this 8.3855? Is the entropy generated because of mixing. So in the other sense is you need to do some work for separating out these two gases again. So this is, it's not a reversible process, it's an irreversible process. So you cannot separate the gases. You have to do some work to separate these gases back again as two gases. So that is this entropy generated. So basically this is because of entropy of mixing. So any doubt in the previous one? So actually you can find it in another way with respect to volume or your mole fractions. So there's another way of finding it, entropy of mixing, but I'll stick to this. So if there is no doubt, I'll proceed to the next one. We have a steam which is at 7 megapascal and 450 degrees Celsius. This is 450 degrees Celsius. That degree is converted into heat. So this 450 degrees Celsius is throttled in a valve to a pressure of 3 megapascal during a steady flow process. Determine the entropy generated during this process and check if the increase in entropy principle is satisfied. So we need to find out, in a valve the gas is expanding, and you have to see whether this causes an increase in entropy, or we know that this is an irreversible process. You have to prove that it's an irreversible process. We say that entropy will always be increasing, and we have to show that this can happen. So physically also we know that we are from 7 megapascal, which is higher pressure, you are expanding to 3 megapascal. So the work which you can do with 7 megapascal and work which you can do with 3 megapascals are different. So 3 megapascal is less, so there is always an entropy generation. So this we have to prove it. How do we prove this? So we know when we do a steady flow energy equation for a valve, so what we get is your enthalpies are constant. So enthalpy in is equals to enthalpy out. So if you remember the steady flow energy equation, SQ minus W plus mass of energy of with mass n coming in and the energy which is going out equals the change in energy of system. So here change in energy is 0 because it's a steady process. So and Q and W is also 0. There is no heat and work interaction with valve. It doesn't generate work and there is no heat. So we have the energy coming in with the fluid which is coming in and the fluid energy which is going out. So when we neglect the kinetic and potential energies, so what we get is enthalpy in is equals to enthalpy out. So this process is basically an isenthalpic process. So enthalpy remains constant in expansion in a valve. So from a steam table, so this is steam. So from a steam table for pressures of 7 megapascal and 450 degrees Celsius, we can find out that enthalpy at state 1 is 3288.3 and entropy 6.6353 kilojoule per kg Kelvin. So next is state 2. So we know one property which is 3 megapascal. To locate a point, you need basically two values. So that's a two property or rule or to find a state point. So here we know pressure. The next is your enthalpy. We know that the enthalpy is constant, so that is the enthalpy is known. So now we know two properties to locate the state of this state 2. So now state 2 is 3 megapascal and enthalpy is 3288.3 kilojoule per kg. So from there we can find out entropy is 7.0046 kilojoule per kg Kelvin. So now when we do an entropy balance, so S in minus S out, which is the rate of entropy transfer plus entropy generated equals entropy of system, change in entropy of system. Since this is a steady state, so ds by dt is 0. So Sgen is m dot S1 minus m dot S2. So here there is additional that Q surrounding by T is missing because there is no heat transfer. So that will also be 0. So the entropy generated is nothing but your entropy going out minus entropy coming in. So which comes out to be 7 minus 6.63, which is 0.3693 kilojoule per kg Kelvin. So this is the entropy generated, and since this is positive, we know that the principle of increasing entropy is true, and this is because it is unrestrained expansion. So there is no restricting, and you are not overcoming anything. So with the pressure, so I'm just wasting the pressure with expanding. So the increase of entropy principle is obviously satisfied during this process, and entropy generation is positive. So this was a fairly simple problem. Any doubt? If you have any doubt, you can ask anytime. So moving ahead. So the next question is, a steel casting specific heat of 500 joule per kg Kelvin of mass 20 kg initially at 200 degrees Celsius is to be cooled to room temperature of 27 degrees Celsius. So it is first kept in a furnace that is maintained at 140 degrees Celsius and then moved to a water bath that is initially at room temperature. So what you have is a steel casting. So you're doing some manufacturing process. You've casted an item, and you know that the specific heat of that is 500 joule per kg Kelvin, and your mass is 20 kg. So this is initially at 200 degrees Celsius, and you have to cool it to the room temperature. So what you do is this cooling is happening in two processes. So first you are taking this item and keeping it in the furnace that is maintained at 140 degrees Celsius. So from 200 degrees Celsius it will come to 140, and then you are dipping it into a water bath which is at 27 degrees Celsius. So it is happening in two processes. So it is finally allowed to cool in the ambient air. So there is another process. Then you are taking it out of the water and keeping it to be cooled in the air. So now determine the entropy generated during this process. The water bath may be assumed to contain 80 kgs of water. So the specific heat of water is given as 4200, and heat loss from the bath to the ambient may be neglected. So you are assuming a insulated water bath. So this process is happening in 3 steps. So initially, as a constant temperature 140 degrees Celsius cooling, and then then you are dipping it in the water, and then allowing it to be cooled in the air. So there are 3 processes. So we break down and solve it in parts. So first is, let us take the casting as a system and calculate its entropy change and that of the universe during the process. So first is your system. So initially this was at 200 degrees Celsius, and then it is cooling to 140 degrees Celsius. So that is a change in entropy of this casting. So that is our system. So that is MCP ln T2 by T1, and since this casting there's no pressure in this thing, it's only temperature here. So MC, so 20 into 0.5 into ln, so you are substituting temperature in kelvins, and what you get is minus 1.3565 kilojoule per kg Kelvin. So that is your entropy generated, and how much heat is lost to the surrounding or the furnace is MC delta T. So that is 20 into 0.5 into your temperature difference is 200 minus 140. So this gives you 600 kilojoules. So 600 kilojoules of heat is lost to the furnace in the process of cooling it to 140 degrees Celsius. So the entropy generated in the surrounding. So system we calculated, which is minus 1.3565, and surrounding is at 140 degrees Celsius now. So your furnace is surrounding for the casting. So that is at 140. So Q by T. So Q is 600 and the temperature is 140. Substituting it in kelvins, we get delta S of surrounding is 1.4528 kilojoule per Kelvin. So if you see, delta system plus surrounding just for this process is positive. So next is you are dipping this into a water bath. So, and what's happening here is your casting, which is at 140 degrees Celsius initially, when you are dipping it in water, it cool down and simultaneously it will heat the water. So since this is insulated, so the water temperature will rise to, and they will reach an equilibrium temperature. So we need to first find out this equilibrium temperature. So what we know is MC of the casting and MC of the water and initial temperatures. So doing an energy balance, there is no heat transfer and there is work transfer. So your internal energy is same. So equating this internal energy change of the casting and the water, we can find out the temperature. So that will come out to be 30.266 degrees Celsius. So that is the final temperature. Sorry, there is a small error here. You have to substitute this in Kelvin. Your C is given in kg per Kelvin. So 500 joule per kg Kelvin. So you have to substitute temperature is also in Kelvin, or else this will not get cancelled. So there is a small error here. So but either way it gets 30.266. So next is delta S of system. So delta of system is again the same MC ln T2 by T1. So we know the initial and final temperature of the casting and the water. So we can find out the entropy change, and it will come out to be minus 3.088, and for surrounding is 3.638. Both is MC ln T2 by T1. Then now from this temperature of 30.2, you are allowing it to cool to the ambient temperature of 27 in the air. So we know MC ln T2 by T1 again for the system comes out to minus 0.1083 kilojoule per kg Kelvin. So the heat transfer to the surrounding in this process is you can estimate Q is MC delta T, which comes out to be 32.66, and similarly surrounding is at temperature 27, So entropy generated in the surrounding is Q by T is 0.1089 kilojoule per Kelvin. So this is a constant temperature. In previous case, the step 2 is it was in water and the water temperature was varying. So we did NCl and T2 by T1. Here the surrounding and it's a constant temperature. So this is your delta S. So summing up all of this entropies of system and surroundings, we'll get the total entropy produced during this cooling process. So that is delta system plus surrounding of all. It will come out to be 0.64669 kilojoule per Kelvin. So that is the entropy generated because of this cooling process. So any doubt in this? Okay. So moving on, it's the next question. So this is not a control volume but a control system. We'll see how to solve this. So we have a container with a mass m of oxygen which is moving horizontally on wheels as shown in figure. So this container is subjected to following processes. So 1 to 2, very slow acceleration from the state at rest. So very slow acceleration. So slow means they are trying to achieve a reversible process, so like a quasi-static process. So there is a reversible process, not generating any internal entropies. So from state rest to constant speed at C2. So now, so you have a vessel containing oxygen. So what you are trying to do is you are slowly accelerating it. So such that you don't feel that jerk anything. You are moving, starting very slowly and accelerating very slowly, and it's taking some time, a large time, to achieve a state having a speed C2. Then this vessel is going and hitting a wall and coming to a stop. So now the velocity is reduced to 0. So this is the two processes happening. So slowly you are accelerating and reaching a speed C2, and then going and hitting on a wall, and so you are trying to crash it and bring it to a stop. So that is the second process. So what is being assumed here is your container and the wall are infinitely rigid. So what it says is even if it goes and hits the wall, the vessel is not damaged. So that's what we are trying to show. So the normal accidents which you see in roads, you go, the car crashes and it crumbles. So that the energy which is the momentum and energy that is transferred to the car body, and the car crumbles, or else that whole energy comes on to the driver, and the driver will feel the shock, and he may have injuries. So that you don't want that. So you design a car such that it crumbles, the body absorbs that momentum change and the energy which is happening because of the crash, and the driver is safe. That's what is want. So this is, you see, it's equivalent to that. So you have this vessel, you are going and crashing it, but the vessel is not getting damaged. So having the case, your car is going and the car is not damaged. The car you have designed it so good that the car will not have a dent. So it hits the wall, so there is no dent, but where dissipating that energy. So it goes into the person who is driving it. So this is similarity to that, you see. So what is the assumptions which you are taking here? So your container and the wall are infinitely rigid, so there is no damage to the vessel. Then the container is thermally insulated, so there is no heat transfer from the vessel. So these are the two assumptions which you make, and what you need to find out, what is known and what is you need to find out is, so initial temperature of oxygen is at 20 degrees Celsius. So and second is an isochoric specific heat of oxygen, which is given as 0.6496 kilojoule per kg Kelvin, and the mass of oxygen is 0.1 kg, and the speed of the container at state 2 is 100 meters per second. So with this we need to find out determine the evolution of internal energy and of the total internal energy of the system. To determine the evolution of the temperature, and is the process reversible? So what's happening is you have to find out how the entropy is changing of the system, and your temperature and your internal energy. So that's what has been asked. So first is the case where you have your vessel is slowly accelerated and it reaches a constant speed c2, which is 100 meters per second. So how the internal energy is changing? So process 1, 2, you have, since this is insulated, so there is no heat transfer, and since this vessel is rigid, so there is no work transfer also. You see, it's just accelerating and there is no work transfer. So your dV is 0. So your change in internal energy, du is equals to Tds. So from the first law, Q minus W is du. So the acceleration being slow from state 1 to state 2, so there will be no internal friction. So basically it says there is no entropy which is generated. So the molecules are staying, and because of acceleration you are not feeling them. So jerk, and which is not the friction is not felt. So your ds is 0. So the first case, the oxygen, so there is no change in internal energy of the oxygen. So oxygen will be at the same temperature. So the second is the change of total internal energy, that is according to the fact that potential in the system does not vary. So you are at constant plane. So but you are accelerating and it is reaching the some velocity. So you have a kinetic energy. So this system, you are having two parts. So one is your oxygen and one is your vessel. So the system internal energy changes your change in kinetic energy. So just like applying energy balance, your du is equals to dE. dE is multiple parts. You have in potential energy, kinetic energy, and with respect to temperature change, and so on. So here, because of the kinetic energy, the change in internal energy of the system, the total energy of the system is mv square by 2, or your velocity is 100 meter per second and mass is 0.1. Substituting, we get 500 joules. So that is the change in internal energy of the system. Next is evolution of the. So next is the process 2, 3, where you're crashing onto the wall and coming to a stop. So here too, what's happening is this insulated, your Q is 0, so there is no heat transfer, and then since this is rigid, even though it bends and crashes, there is no change in volume. So there is no work which is being done on the vessel. So your work done is also 0. So what this says is your internal change of the system now is delta U is 0, because Q is 0, W is 0. So delta U is 0. So we have calculated previously. So your internal energy change is 0. So where is this energy which is there? So previously you saw that energy was in form of a kinetic energy. So where is this energy has gone? So this has went inside the oxygen. So is what I was giving you an example of the car crash. So if the car is not crumbling, so you feel that energy. So you will go into injury, damaging the driver. So he may have a fatal injury. So that energy comes to the driver. So similarly, since the vessel is not getting damaged, the kinetic energy which was possessed by the system, that energy is transferred to the oxygen, and the oxygen takes up that energy. So the change of internal energy is therefore your change in internal energy of the oxygen equals to the system, which is internal energy of the system, which is 500 joules. So this comes, your internal energy of the gas is 500 joules. So now how the temperature is changing? So initially oxygen, there is no internal energy change, so your temperature is temperature change is 0. So whatever temperature it was there at 20 degrees Celsius, at stage 2 also it will be at 20 degrees Celsius. So after crashing, so now the oxygen has taken up all the kinetic energy. So there is a rise in internal energy of the oxygen. So that is 500 joules. that is equal to mcv delta T, and substituting that m and cv, you can find out the change in the temperature, and comes out to be 7.697. So your oxygen now is at temperature of 27.7 degrees Celsius. So that's the main idea. So that the trick part here was the energy dissipating, where that energy is going. So that was the tricky part here. So next is very much whether this process is reversible. So here you see I have shown how the process is happening in a U and S US chart. So we have access to a vertical and roughly with a horizontal axis. So initially at 1, your that is your oxygen. It is at state 1, and it's not temperature is not varying, but the energy processed by the system is at state here, the circle point here, UC3 or U3. So that is the energy processed by the vessel at state 2, because there is a rise in kinetic energy. Then what is happening is it comes to an abrupt stop. So the your total internal energy stays same. So it comes to state 3, so that is the same energy level, but the oxygen takes away that energy and it goes from 2 to 3, the bold line. So that's how oxygen goes, and there is a rise in entropy. So but this is a constant U process, because your whole system internal energy is same, and it is just getting converted from one form to another. So initially at 1 to 2 there is entropy change is 0, then from 2 to 3 your entropy changes mcv ln T2 by T1 or T3 by T2, which comes out to be 1.684 joule per Kelvin. So this says that your entropy is increasing and your principle of increasing entropy is true, and this is not a reversible process. So which makes sense, it will not be a reversible process. So any doubt in this? Sorry, I didn't see the question. You want to ask, want to explain the question again. So so there are two questions. I'll answer this now. First, starting the what's happening is you have a vessel which is insulated and rigid. So insulated, there is no heat transfer, and rigid means the volume doesn't change. So even you hit it with a hammer or something, there will be no change in volume. So it is that rigid. So that says that this doesn't volume, there is no change, because rigid is the other way of saying it is it doesn't do any work. So there is no work interaction that can happen with this vessel and the surrounding. So that's what they mean by rigid. So you have this, and you have oxygen inside. So this vessel, initially you accelerate it very slowly. So very slowly in sense that it's reversible. The process 1 to 2 is reversible. So it's like you're accelerating it, you're pressing your accelerator very minimum, so that it the car moves basically, like your vessel starts moving, and you're doing it for a long time. You're not changing the accelerator, you're having it at a very small pace, and you are taking a large amount of time to come to 100 meters per second. So that's what they say, very slowly doing it and bringing it to 100 meters per second. It's another way of saying that this is a reversible process. So it's just like you're pressing it minimally and you're coming it to a stop. So this is an idle assumption. So we're saying that this is a reversible process. Then the second process is, after reaching a constant velocity of 100 meters per second, you're crashing onto a wall and bringing it to a stop. So that's the question, and you have to find out the entropy change, how the temperature is changing, and how the internal energy is changing. So is it clear? Okay. So your another question was to explain isentropic efficiency. I think I'll take up questions on next week, so it will be easier to this thing. But just to give you an idea, so you are doing a process, either compressing it and or expanding it in a turbine or a compressor. We know a reversible process. If you consider reversible process, uh, that will take up minimum amount of work to compress a fluid, or when you are expanding it, that will give you a large amount of work when you are doing it a reversible process. So again, what is this reversible? So you are not expending your energy in overcoming friction. So assume a case where you have a compressor and it's totally frictionless. So an ideal case, it's a super efficient compressor. So when you're compressing it, there will be no change in entropy. That's what you say. You're compressing the process. There is no change in entropy. But ideally, in the practical case, that doesn't happen. So you have bearings. There is a friction there, and there are valves and other stuffs. And if you have a piston compressor, your surface which is in contact with the cylinder. So these all add up friction, and your fluid itself will have its own friction, viscosity and so on. And there is a heat transfer. So there's multiple phenomena each comes into play, and they generate entropy. So this isentropic efficiency is an idea to equate how off we are, or how much different our work is compared to a reversible process. So to equate that, we do something called as an isentropic efficiency. So for a compressor, we know that reversible process will take up minimum work to compress a fluid, and our practical case which we see is we are putting in more amount of work to compress the same states, pressures, to compress it to a same pressure. We are putting in more work. So this isentropic efficiency for this compressor is in now your ideal and reversible case work done divided by your actual work. So that is the efficiency. So that says how much we are off from the ideal case of a reversible process. And similarly, for a turbine where you are generating work, so reversible work will give you the maximum work, and again, so the friction and all will takes away some amount of work, and you will get very less work compared to the reversible work. So again, there this efficiency is equated. So ideally, what you should get and how much you are getting. So to do that, because it's difficult to find out this entropy in actual case, so we use an efficiency formula to overcome this calculations and tedious work. So then in case of turbine, it's the reverse. So your work which you are getting divided by the actual reversible work. So compressor, it's different. It's the other way around. And the turbine, it's the so that you have to be careful. So that is the idea of isentropic efficiency. So your question is isentropic turbine is proportional to isentropic compressor. So see, if your turbine, if you are running it in reverse, so it's basically the same. Yeah, correct. Inversely proportional. So if you are the other way of saying is you are compressing and expanding this, you can use the same this thing. But practically the blades and other stuffs, angles and matters. But in ideal case, you can assume. But your point was in terms of the values. Yeah, it is inversely proportional. There it is. So you remember what you are getting it out. So you're in compressor, you are doing more work, so it will always be the denominator. So your efficiency is always less than 1. So whatever may be the efficiency, it will always be less than 1. So with that in idea, so compressor, you are giving in work, so you have to give more work because of friction. So that will be the denominator. And in turbine, you will get work, and that turbine has to overcome friction, so you will get less work. So that will be at the numerator. So with that, I think you don't have to remember this inversely and so on. You have to remember just this efficiency will be less than 1, and what is done to overcome friction. So in that sense, what is lower will come in the top. So I hope this is clear. sorry. So we'll break down this now. I hope now it's clear, audible. Okay. So you have a closed rigid tank, and this contains 5 kg of air, which is at initial pressure and temperature is given. So now you have a stirrer inside, and you have that vessel is in contact with the constant temperature source. So there is a heat transfer which is coming in at from the 600 Kelvin temperature source, and you are doing work with the stirrer, which is equal to 600 kilojoule, and because of this, the air temperature is rising, which is there inside the vessel, to 600 Kelvin. So you need to find out how much is the entropy transfer to the air and how much is the total entropy produced. So this is the process which is shown here. So initially the air, which is at 300 Kelvin and 1 bar, is going to some pressure 2, because it's a closed vessel and you are doing work, so that is getting converted into pressure. So you are heating it up, so your temperature is increasing. So for constant volume, your pressure will increase. So for constant volume, your pressure will increase. So you are at pressure at P2 and your temperature is 600 Kelvin, and you are going this across a constant volume process because it's a closed system. So we need to now, with this known, we will see how to calculate the entropy change. Now, since the volume is constant for the closed system, V2 equals V1. Therefore, by the ideal gas equation of state, P2 is T2 by T1 into P1. So that is your P by T is constant. Since V is constant from ideal gas equation, your P by T will be constant. So that's what we have written, and we are finding out the final pressure. So our temperature is 600 at final temperature, divided by initial temperature 300 into the final pressure. It gives you 2 bar. So now we know the final pressure and temperature. So now we can apply an energy balance across the control volume. So there is heat transfer and there is work transfer, which will give rise to change in internal energy. So delta U is Q minus W. So now, since we know the initial and final pressures and temperature, we can find out how much is the energy change, internal energy change, and we also know how much work is being added with the stirrer. So Q is mCV T2 minus T1 plus W. So substituting, you know mass, how much mass is there, 5 kg, and you know CV, which is 0.733, and also the temperatures, initially 300 and final 600. So substituting it here, and the work, which is 600 kilojoules, which will give you to 499.5 kilojoules. So now, so this is equal to the heat which is added to the control volume. Now with this we know the heat source temperature, and we know how much heat is added, so we can find out the entropy change because of the entropy transfer with heat because of heat. So we know the source is at 600 Kelvin, so we can if you see the entropy balance, the d entropy change with respect to time equals entropy coming in and going out plus the Q surrounding by T, so minus Q surrounding by T plus the entropy generated. So there we know Q surrounding by T, which we have found out here, is 0.8325 kilojoule per Kelvin. So this is what we get, S2 minus S1 is Q by TB plus sigma. So substituting it and balancing it out, we can find out the entropy generated. This M S2 minus S1 minus Q by TB. So the change in entropy can be calculated for constant specific heat. So since the volume is constant, so S2 minus S1 is CV ln T2 by T1. So substituting the temperature values, and you can find out the entropy change. So entropy change comes out to be 0.5081 kilojoule per kg Kelvin. So now calculating these values, we can find out sigma by the M S2 minus S1 into 2.7079, which is the entropy change in the system, plus your surrounding, which is 0.8325. So this comes out to 2.5404 kilojoule per Kelvin. So this is the total entropy. So you see, have two parts. Here this is heat coming into the system, so that is increasing the entropy of the system, and the one which is the surrounding, which is losing the same amount of Q. So you should add both. So you should be careful in that. So that comes out to be S2 minus S1 is 2.5404 kilojoule per Kelvin. So any doubts? So this is my last question. That will finish for today. So this is analyzing a heat pump and how entropy is varying for each of the components. So we'll see how to solve this. So we have components of heat pump for supplying heated air, with building air are shown in the schematic below. We have this schematic here. So this is a heat pump. So this is similar to a refrigerator, but cooling is not your priority, but the heating. You are trying to heat volume, control volume. So this is what is happening. So you have compressor, condenser, expansion valve, and evaporator. So you are compressing it and you are rejecting heat in the condenser, which is used to heat up whatever your requirement is. So your air is coming at 20 and going out at 50, and then you are expanding in the valve and going to the evaporator. So this is your process. So at steady state, refrigerant 22 enters the compressor at -5 degrees Celsius and 3.5 bar, and is compressed adiabatically to 75 degrees Celsius and 14 bar. So this is your compressor enter and exit. Next, from the compressor, the refrigerant passes through the condenser, where it condenses to liquid at 28 degrees Celsius and 14 bar. So that is your now the condenser is coming at 75 and 14 bar, and it is going out at 28 degrees Celsius and 14 bar. So it's a constant pressure problem. So the refrigerant then expands towards bottling that to a 3.5 bar. The state of the refrigerant is shown on the diagram. So return air from the dwelling enters the condenser at 20 degrees Celsius and 1 bar with a volumetric flow rate of 0.42 and exits at 50 degrees Celsius with a negative change in pressure. So now we need to find out neglecting potential kinetic energy, the rate of entropy fraction in condenser, compressor, and expansion valve, and discuss whether irreducibility in the components, source of irreducibility. So this is how the process looks in this diagram. So initially you are at state 1, which is -5 degrees Celsius and 2.5 bar. You are compressing it adiabatically. So this is the adiabatic process, and then the entropy stays same for quantity. So getting compressed adiabatically. Then so it's not reversible, it's compressed adiabatically. Then at state 2 is at 75 degrees Celsius and 14 bar. Then there's a constant pressure heat rejection in the condenser, and you are coming in at 28 degrees Celsius and 14 bar, and then you are expanding in valve, which is 3 to 4, and 4 to 1 is again in the evaporator. But here we don't need to consider evaporator. So only idea is to see compressor, condenser, and valve. So at inlet to the compressor is at -5 and 3.5 degrees Celsius. So it's like steam table. We have this refrigerant properties table. So from there we can find out S1. So the idea is same. It's like using a steam table. So only the fluid is different. So here for this temperature and pressure, the entropy at this point is 0.9572. So similarly at state 2, so the refrigerant is now superheated at 75 degrees Celsius and 14 bar. So interpolate enthalpies. You know the saturated vapor and saturated liquid enthalpies, so you can find out the vapor fraction here. So X4 is H4 minus HF4 is the saturated liquid divided by the latent heat, your saturated vapor minus saturated liquid. So that gives you the vapor fraction of 0.216. So similarly, you can using this and your entropy of saturated vapor and liquid, you can find out the entropy at that state 4, which comes out to be 0.3078 kilojoule per kg Kelvin. So that is your entropy there. Now we need in the considering the condenser, we are doing an entropy balance across the condenser. Since this is steady state, change in entropy of this condenser is 0. So your entropy generated is equal because of the mass coming in and mass going out. This is m dot ref coming in as S2 and going out at S3, and mass of air is coming in at S5 and going out at S6. So for initially we need to find out the mass of air, which is area into volume divided by specific volume, and specific volume is nothing but we can find it from the ideal gas equation, P by RT. So substituting all the values here, AV is the volume flow rate, this is 0.42, and the pressure and temperature you are substituting, we get mass of air as 0.5 kg per second. Then similarly, mass of refrigerant is mass of air. You're doing an energy balance across the condenser, is the heat rejected by the refrigerant is equal to heat gained by the air. So mass of refrigerant into enthalpy change of refrigerant equals mass of air into enthalpy change of air. So mass of air into enthalpy Cp delta T. So 1.005 into change in temperature, and similarly enthalpies we know at condenser inlet and exit. So substituting, we get mass of refrigerant as 0.07 kg per second. So similarly for this process, so entropy of air, your pressure is same. So the entropy generated is because of the temperature change. So S6 minus S5 is 1. Cp into ln T2 by T1. Substituting it to 0.098 kilojoule per kg Kelvin. And similarly, substituting the values for refrigerant, ln T2 by T1. Plus, you have to also be careful here. So here entropy change is happening two ways for the refrigerant. One is the temperature change, and there is a latent change, latent heat. Because of that, there is entropy change, but this is happening at constant temperature. So which we have already calculated. S3 is known, and S3 is equal to your saturated vapor liquid enthalpy, will not change much. So that's what we have assumed here. S3 is saturated fluid 28 degrees Celsius. So initially from 75 degrees Celsius to this 28 degrees Celsius saturated vapor. So that is your entropy change because of temperature change, and then additional entropy which is because of this phase change. So you have to include that. So that's what we have done here. So m dot into your entropy change plus 0.5 into your air entropy. So but here you can directly, since we know entropy at state 2, we can directly find out the entropy change. So but if we have to calculate the other way, from we don't know entropy, we can estimate, so but we have to find out with temperature. So you have to find out Cv ln T2 by T1 and then add your latent heat divided by the temperature. So that's the other way of finding the entropy change, just to give you an idea. So but since we know the entropy at inlet and exit, we can straight away find out the entropy change here. So this comes out to be entropy generated in condenser as 7.95 in 10 power minus 4. Similarly for compressor, your sigma compressor is again there is no heat transfer, and since it's adiabatic, and work transfer doesn't constitute entropy change. So your sigma compressor is entropy change in of the fluids. So m dot refrigerant S2 minus S1. So substituting the values, we get 17.5 and 10 power minus 4. And similarly the valve, we have found out the entropy at exit, and we know the inlet, so that gives 9.94 in 10 power minus 4. So you see, this is the entropy generated in each of the components. So entropy production in the compressor is due to fluid friction, mechanical friction of the moving parts, and internal heat transfer. So that's what I explained when I was discussing about the efficiency, isentropic efficiency. So next is for the valve. This is basically because of the fluid friction and the expansion, because you are not generating any work, straight away expanding it. It's like a free expansion. So that is necessary because of this fluid friction. Then the principles of in your condenser is because of the heat transfer happening at a different temperature level. So your fluid refrigerant is at some temperature and your air is at some temperature. So because of this temperature difference, the heat transfer is causing an irreversibility. So that is, so we cannot make it zero. We actually make it like a Carnot system when you do it at constant temperature, and then it becomes reversible. But in practical case, that cannot happen. You need a certain temperature difference to have a heat transfer. So this temperature difference is what is causing primarily the irreversibility in the condenser. So here, if we assume there is no pressure drop in the condenser or in the evaporator or in the air side, but in actual cases there will always be pressure drop, and that will also add irreversibility. So that is again because of the fluid friction and friction between the fluid and the surface and so on. So with this I have completed what I prepared for today problems. So if you have any questions, I'm happy to answer. So I hope there is no question. So we'll see similar set of problems the next week also, based on entropy. Okay, if there is no question, we'll end the session. Thank you for joining. I'll come up with some other questions, different set of problems. No, assignment will be different. Assignment set of questions will be totally different. That you have to solve. So you have to solve each of the assignments. So that and this are totally different. This is for your better understanding. I have prepared some problems for you to understand it better, and you can. This is also a discussion where you can ask questions. I'll be sharing this slides, whatever file is there in a drive, and you will get that link, so you can access it anytime. Okay then. Thank you for joining. We'll see you next week.